This is a worked example on how to graph a Laurent monomial using function transformations. So usually for a worked example, I would choose an easier problem, but this one's a bit trickier and I really want to make sure that you can fully understand how to do a problem like this in case you see something like that on an exam. So the thing that makes this problem tricky is that up here at the top, I have the form in red that we want to have our function in before we can actually go through and identify the values of h, a, and k. But the function we're given is not in this form. So we have to do a little bit of extra work to kind of put it in the form we want. And the way we can do this, at least in this scenario, is with synthetic division. So what we can do is we can take our functions and we can divide them. So this won't be very hard, right? X times 2 gets you 2x. Then I have plus 2. You can flip the signs, cancel these, and I get negative 3. So I divide, I get 2 with a remainder of negative 3. If I write this out in one of the forms, I get this. But a different form in which you can write synthetic division is you can actually divide this entire result by x plus 1. And this kind of rearranges the function to something that we can work with. So if I divide this entire function by x plus 1, I will end up getting 2 minus 3x plus 1, right? And so this actually is a lot closer to the form that we want. And if I do a little bit of rearranging, I can swap the position of the 3 and the 2, and then I can actually bring that 3 out front. That is really messy. Let me write that neater. I can actually bring that 3 out front, and we can see that the values of A, H, and K are now more readily identifiable. So that's kind of like a way that you might not sneak, but that you might take a function and put it into the form that you want. And there are other ways that we can do this, but I just wanted to show you an example of how that works. So now that we have this new function, and by the way, if you still want to take a look at my long division, please pause the video now. I'm about to erase. But now that we have our function in a form that we can work with, we can actually go through and identify those values. So let me just put a little equal sign so we know that is the same function. Now we can kind of make our table, right? So give me a second to draw this out. Okay. And now I can choose my sample points. So these are my points. And in the worksheet, I gave a list of example points that you can use for both even and odd functions. Our function here is odd because the term x plus 1 is raised to the power of 1. So the sample points that I'm going to choose are negative 1, negative 1, 0, 0, and 1, 1. And so now I can go through and identify those values of h, a, and k. So I usually write h equals, a equals, and k equals. H is the tricky one that you want to watch out for. So in the original formula, we have x minus h, but here we have an x plus h. And to pass between the two, I want to pick a value of h that gets me a plus 1. And so if I have x minus negative 1, that gets me positive 1. And so the h in this case is negative 1, then a is negative 3, and k is positive 2. So those are our values. Now let's just go through and apply theorem 3.2. So I can take my h value and add it to all my x values. So negative 1 minus 1 is negative 2. 0 minus 1 is negative 1. 1 minus 1 is 0. All the y values stay the same. Now I can take that value of a and I can multiply that by all my y values. So let me copy over the x values first. Okay, negative 1 times negative 3 is positive 3. 0 times negative 3 is 0. And 1 times negative 3 is negative 3. And then lastly, I can take that value of k and add that to all of my y values as well. So again, I will copy over my x values. Now 3 plus 2 is 5. 0 plus 2 is 2. And negative 3 plus 2 is negative 1. Okay, so now we have a list of points over here, and those were on our original function, and we now have the resulting points over here that are on the new function. And really quickly, let's just take a look at where our sample points ended up. So let me just draw a really rough graph. This doesn't need to be neat. And keep in mind that that function of 1 over x, our parent function, the sample points we're choosing from are right here, that's 1 comma 1, right here, negative 1, negative 1, and then we actually did an interesting move. We chose a point which is not in the domain of our function, 0, 0, but we're going to use that to track the location of the asymptotes, if that kind of makes sense. So our new function, and I can draw a much neater graph this time. Oops, sorry, I thought the straight line was going to work for a second. Okay, so in our new graph, now we can kind of go through and build the look of that function. So, okay, let's see. We're going out to positive 5, so I want to put 5 tick marks so I have enough room. I guess I'll put 5 on each axis. Okay, now let's graph those points. So first, negative 2 up 5, and that's going to be up here. Then we get negative 1 up 2. That's going to be right here. And then we get 0, negative 1. Okay, so now we have our points, but we want to be more careful with how we're drawing this, right? Okay, so let's keep 2 facts in mind, and they both revolve around the a value. The first is that a is 3, or at least, well, it's negative 3, but let's just focus on the 3 for now. So this function is going to be stretched 3 times taller than it normally is. But also, it's going to be flipped along the x-axis. So this behavior over here, where you have a tail in the top right quadrant and a tail in the bottom left quadrant, that's kind of going to flip, and we'll have a tail in the top left and a tail in the bottom right. Before we even do that, and let me see, okay, I don't want to mess around too much, but let's keep in mind that stemming from this center point we tracked is where our asymptotes are going to be. So I can actually, I'll do it in a different color just so it is clear. I can actually draw vertical and horizontal lines coming out of this point because those lines are going to be my asymptotes. Then I can remove them later so it looks neater. Now, all I want to keep in mind is the fact that those tails flipped locations and that my function doesn't really want to touch the asymptotes. And because of this, oops, sorry, let me change colors. And because of this, I can start my function down here. It's going to travel this way. It doesn't really want to touch the asymptotes, so it's going to start traveling up, cross that point, and then continue over to infinity. And then same thing down here. I can kind of start it along the asymptote, start drawing upwards. Okay, it doesn't want to touch that asymptote, so it's going to cross this line and go up towards infinity, just like that. And so obviously this graph is like very sloppy. It doesn't look good at all, but it does sort of offer a kind of design for the function, right? In reality, this should be a lot sharper. Up here should be a lot steeper to kind of match that point. But the general idea is that we can take those 3 points, we can track things out, and we can draw a decently accurate graph of what this function will end up looking like. So that's the process of graphing a Laurent monomial if you're given a form that doesn't necessarily look like what it should be. But again, the lesson here is that you can put it into that form, or at least that's the goal. You should be able to, and once you get it into that form, it's just kind of that process of A, H, and K that we're used to.